Good morning, everyone. So, welcome to the Learning Factories on bio-based thermoplastic processing and material reprocessing. My name is Silvia Cruz. I'm currently responsible for the advanced manufacturing process for polymers area at PIEP. It's a Center for Innovation in Polymer Engineering. I hold a PhD in Polymer and Composite Science and Engineering from the University of Minho, where my research focuses on developing sustainable solution applications and technologies related to conventional and non-conventional injection molding. Today's training brings together researchers, professionals, students to explore innovative technologies that are shaping a more sustainable plastic industry. Sorry. So the event is organized within the framework of Vital Project, which develops innovative processing solutions for bio-based foam thermoplastics across three main processing value chains: 3D printing, bead foaming, and foam injection molding. These technologies are being explored across several industrial sectors, including automotive, home appliance, and marine, where lightweight, recyclable, and bio-based materials are increasingly essential for achieving circularity. Vital also focus on enable commercially viable closed-loop mechanical recycling and on integrating digital tools and artificial intelligence-based process control to optimize the foam injection molding process. While Vital explores multiple processing routes and their uptake across polymer processing value chains, today the Learning Factory concentrates on injection molding line, specifically foam injection molding, and on associated recyclability and digitalization challenges and opportunities. By aligning with the Vital Project ambitions to accelerate the transition to sustainable, circular, bio-based thermoplastic value chains, we aim to provide you with both theoretical foundations and hands-on tools for film process optimization and material reprocessing. So let's begin this collaborative journey toward a circular, smarter future for polymers processing. So let's take a quick look at today's agenda. In the morning, we will have online theoretical sessions introducing bio-based materials, foam injection molding, recyclability, digitalization in foam injection molding, and industrial foam injection molding applications. At the afternoon, we'll have the practical sessions. So to start our program, Lati Johanna will set the foundations by exploring the world of bio-based thermoplastics. Dr. Lati Johanna holds a Master of Science and a Doctor of Science in Technology in Paper Converting and Packaging Technology. She works for over 20 years as a scientist and lecturer at Tampere University of Technology in Finland. Currently, she is a senior scientist at VTT Technical Research Center of Finland, where she has been for more than 3 years focusing on sustainable materials and products. Her research interests include the processing of thermoplastic polymers, extrusion, coating, film casting, and the development of packaging materials. Dr. Lati has participated in numerous national and international research projects and has authored over 60 scientific publications. Let's welcome our first speaker from VTT. Johanna, please, the floor is yours.
Thank you, Silvia, for the kind introduction. Let me see if I can share then my presentation. Let's start with this introduction to the topics of today. So, like mentioned, I am Johanna Lahti from VTT, and I work here as a senior scientist. And I have been working in this vital project, which is organizing this learning factory today. And this vital project, as Silvia mentioned, is about innovative processing technologies for bio-based foam thermoplastics. And this is also the topic of this learning factory. We will talk about different thermoplastic materials, but especially about the processing in foam injection molding. First, I have some slides about Vital project. So Silvia already introduced the main areas of our project and some words about our targets. But these are the details of our Vital project. So we have been ongoing now almost 41 months. So we are finishing the project in next month. And you can see all the partners also on this slide. So we have partners from Finland, Germany, UK, and Italy, Spain, Portugal, and Turkey, and so on. So a lot of different partners representing the whole value chain, which Vital is about. So material producers, processing partners, and then especially the end users who are then exploiting, of course, the developments on Vital project. And VTT has been the coordinator of this project. So main target of Vital project is relating to transition from fossil-based materials to bio-based and recyclable materials. So this is, as we all know now, not an optional thing anymore. It is a strategic necessity. So it is an important thing in development of new materials and how they are processed and what kind of end products we are developing. And in Vital project, we are focusing especially on creating solutions that have lightweight, they are durable, but also recyclable, and especially foamed materials, and also to add bio-based materials. So a lot of different targets in Vital project. And of course, we have different end uses, as Silvia mentioned, 3 different sectors here. So different sectors have different requirements. So this is very challenging project to reach all these targets with these new materials and processes. Here are the main research topics of Vital project. So we do, as mentioned, both material development and process development. So in materials, we have been focusing on PLA and PA. And then in the processing, we have these 3 different processes that Silvia already mentioned. So we have foam injection molding, we have 3D foam printing, and then bead foaming. And we have different partners who are responsible or coordinating these different processes. Then also recycling of the developed materials is very important. And then also we are developing intelligent control systems or digital twins in this project. And on the graph on the right-hand side, you see the main end use areas where we are working. Silvia already mentioned them briefly. So we are working for cruise ship interiors, then household things like fridge parts, and then in the automotive sector, we are working for seat cushions and then body panels of automotive vehicles. Then I am moving from introduction of Vital to introduction of this learning factory. So I will give a very short introduction to bio-based thermoplastics, and then also different foaming methods that are used. So how or why to use thermoplastic foaming in general? Here are collected some things, some positive things what we can achieve with foaming. So for example, with foaming we can improve impact resistance, we can increase ductility, we can increase fatigue resistance. Materials are very workable and they can have very good thermal and acoustic properties. These are properties that we can exploit in many different sectors. For example, those that we are studying in Vital project, but also outside that, for example, packaging area. Then foaming reduces material need. We can reduce processing temperatures needed, for example, compared to extrusion, coating or casting. We use typically lower temperatures. We can reduce energy usage. Then this product weight is very important, so we can create these lightweight structures. And then we can reduce costs through these different improvements that we can achieve with foaming. Then about the foams themselves, we can have different types of foams and we can produce different kind of foams through different processes. So for example, we can have foams with different densities. You can see that we can have very low densities up to very high densities and everything in between. And of course, this we can then have for different end uses. For example, we need to have different densities and then exploit the properties of these different types of materials. Then also the cell size can be different, so we can have so-called nanocellular foams, and then we can have something in between, and then these conventional cell sizes which are over 300 microns. So this is also what makes foaming so good method or process. We can create really different types of materials and structures. So then we can also categorize the foams to closed cell structures and open cell structures, and these also have differences. So for example, these closed cell structures are typically more denser and they are more stiffer. And that is why they are more better, for example, for thermal insulation. They have good moisture and heat resistance, and they have good shock absorption properties. So they can be, for example, used to pack very fragile objects in transportation. Then we have these open cell structures. They are typically more porous and flexible, and that is why they are typically more better for example, flexible cushions and filters and sound absorption. And these structures can be created from different materials through different types of processes. Typically, thermoplastics are used in these closed cell structures, and thermosets more in these open cell structures. But these can be also varied, so different materials can be used in different structures. How we can then affect on the density or the cell size, there are different parameters and means during the processes. I won't go through all the details, but for example, density we can affect with the temperature, and then the cell size can be affected, for example, if we are using some nucleation agents in the process. So there are different things that we can then play with in foaming to create different kind of structures. One very important property for materials in foaming is melt strength. So that needs to be high enough, because if the melt strength is very low, then we cannot create any good foams. Then about these thermoplastic foaming processes, we can categorize them into three different groups. So we have first this extrusion foaming, which is typically used to produce sheet or board or profile shaped products. And this is a process, a special extrusion system, which is requiring, for example, melt cooler for the low density products. I will show you some examples in the following slides about this process. And this is a continuous production process. Then we have bead or particle foaming. And this is a process where we create 3D shaped objects from fused beads. And then for the bead manufacturing, we have different kind of processes available, like suspension polymerization or extrusion. And then also for the bead forming or foaming, we have different processes. Typically, we use steam in this foaming process. And then the third process is foaming injection molding, which is now the topic of this learning factory today, and you will hear and learn more about that today. Then in foaming processes, we use typically so-called foaming agents or blowing agents. And for that, we have two different types of agents that can be used. First, we have chemical foaming agents, and they are inserted together with the polymer granulates in the extruder. And in the extruder, they react at these elevated temperatures, and then we create the foam. And typically these chemical foaming agents are also granulates, or they can be powder format. Both of these agents have pros and cons. Chemical foaming agents are typically easy to use, but they can be quite expensive if we compare to physical foaming agents. And then there can be some challenges to achieve the low or very low densities. And you can see some examples like sodium bicarbonate or citric acid that can be used as chemical foaming agents. Then physical foaming agent is typically inserted directly inside the extruder into the polymer melt as a gas or as a liquid. These physical foaming agents can sometimes be a little bit difficult to use. They require special equipment, for example, if we are using gases. But as mentioned, they are cheaper to use than chemical foaming agents. And with these physical agents, we can achieve wider range of densities compared to chemical foaming. And some examples, once again, for example, isobutane, nitrogen, or carbon dioxide. Then this is a schematic picture of foaming mechanism in general. So you can see the basic structure of an extruder. You can see the hopper there where the polymer granulates are fed. And then if we are using this gas as a foaming agent, you can see that it is inserted almost in the middle of the extruder to the extruder and to the polymer melt. And then these agents that are used as granulates, they are of course fed with the actual polymer into the hopper. And then you can see the different phases, how the foam is created. So the foaming agent dissolves into the melt during the extrusion, and then it creates this one phase solution of the polymer melt and this gas, for example. And what are important parameters during this process is, for example, temperature, what we are using in extrusion, and what is the pressure used in this process. We are affecting the viscosity during this process. So first, the viscosity is decreased And then in the end, the melt is cooled to increase the viscosity. And it is important to follow the pressure during the process so that we prevent premature foaming, because we don't want it to happen too early. Then in the end happens a pressure drop, and then the foaming agent starts to separate from the polymer melt. This separation nucleates the cells or the gas bubbles. The bubbles grow and then stabilize into a foam structure during the cooling process. So the foaming agent is the one that is creating the cell structure and the bubbles. This is a pictures and explanation about extrusion foaming. I don't think I have time to go all the details of the different technologies, but you can later on check through the descriptions of different technologies. But basically, extrusion foaming is a continuous process, and we can use different type of extruders there. We can use single screw extruders, or we can use twin screw extruders. And as explained before, we feed the polymer granulates inside the extruder, and then the screws convey the granulates and melt the granulates with the help of heat and friction, and then we create the foam as explained during the previous slide. And in extrusion foaming, we can use both chemical foaming agents or physical foaming agents. Then in larger commercial extrusion foaming lines, there can be also extruders linked in tandem process. So we can have one extruder after another, and this way create the foamed structure. And in the pictures, you can see some examples from our facilities. So our lab scale single screw extruder creating this extrusion foam, and then a more detailed picture of this foamed material that we have created. These are also pictures of extrusion foaming. So you can see on the right hand side the extruder die where we are creating the foam, and then this round how would I say, big bubble of the material, which can then be collected into a roll like shown on the left-hand side. And here are listed the important foaming parameters. So I already mentioned some earlier. So there are a lot of different parameters that we can play with in foaming, and they affect very much on the foam that we are generating. So for example, melt temperature is very important. You need to know what kind of temperatures you can use with your polymer. Of course, the actual extruder and its geometry affects like what kind of die you have, and its geometry is important. Then the pressure was already mentioned. So how you control the pressure and how it behaves during the process. Amount of foaming agent is one important parameter, and how it is soluble into the polymer that you are processing. Then also the diffusion rate of the foaming agent is important. And of course, the polymer properties. So I already mentioned the melt strength. So melt strength of the polymer that you are processing is very important, and you need to know your polymer, how you can process it. Then we can affect on the process not only with the foaming agent, but also by using so-called nucleating agents. For example, talc can be added along with the granulates to control the cell size and cell density. And let's see how the video works. Here is a short video clip. These are also pictures from our facilities, a little bit bigger line compared to previous one here. So we can already produce this white foamed, how would I say, film, or what would be the correct term, but anyways, a roll of extrusion foamed material. Then the second process is so-called particle foaming or bead foaming, and this is also something we have been studying in Vital project. Fraunhofer has been especially responsible for this process in Vital project. So bead foaming or particle foaming is a batch process where we create lightweight 3D shaped objects by fusing expanded polymer beads together. And this slide contains a lot of information about how the microparticles or micropellets are first produced and how the beads are then processed. I don't think I have time to go through all the details, but here are the processes explain how the beads can be produced. There are also different ways to that. But on the pictures you can see, on the above picture you see the micropellets, and then on the second pictures you see the expanded beads. Here are some pictures also from our facilities regarding particle foaming, and then some pictures of samples, so bead foamed samples. So for example, in the picture in the middle, you see our pilot scale pre-expansion equipment. So we feed the micropellets there, and then we do the pre-expansion, and then we have the steam chest molding equipment to create these bead formed objects. And you see some samples here from different polymers on the lower picture. And then on the right hand side, you see once again first the micro pellets, then the expanded beads, and then the actual foamed objects from EPS. And then, as I mentioned, Fraunhofer has been studying this process in this Vital project, and they have been studying this steam-free process with radio frequency heating. And the benefits of this process is that it uses up to 90% less energy, and it reduces the risk of hydrolysis. And on the last slide, or last picture on the right-hand side, you see one sample or picture of a sample produced through this Fraunhofer's technology. Then I have the final slides about the actual polymers. Not sure if I've already over time, but I will run these through. So this is a picture you have seen maybe many times representing the different categories for thermoplastic polymers. On left lower corner, we see the conventional plastics, and then in these other three sectors, we see the different bioplastics. On the left-hand side, we have those ones that are not biodegradable, and then on the right-hand side, we see the categories of those biodegradable polymers. And then the right top corner is the one representing biodegradable and bio-based polymers. And you see some examples of polymers from these different categories. And of course, we can use different biopolymers also in foaming processes. And these have also been studied in Vital project. And of course, when we are shifting from fossil-based materials or products to bio-based, these bio-based and biodegradable polymers are more and more studied also in foaming. So for example, here is polylactic acid mentioned first, and this is maybe one of the most researched biopolymer in foaming, or has been mostly studied. And as we know, it is a bio-based material, bio-based polymer, and it is industrially biodegradable. It has some challenges, or it has some typical properties. So it is very stiff, it can be brittle. So these can be challenges in some cases. Melting point you see there. Some challenges with melt strength sometimes in foaming, and this can be affected, for example, with blending with some other polymer or by using chain extenders. And in Vital project, we have been studying, for example, PLA blend from Floreon in these different foaming processes which we are using in this project. So in 3D foam printing, in bead foaming, and in foam injection molding. Maybe you will hear about that later on. Then we have polycaprolactone mentioned here. Maybe I will skip that and go further. Polyhydroxyalkanoids, PHAs, very interesting group and studied a lot. Not maybe so far that much in foaming, but in other sectors, for example, packaging sector, very interesting polymer. It is bio-based, biodegradable polymer, but it can have some challenges in foaming. So it has high crystallinity, it has slower melt strength, so that can cause some challenges and in foaming process. So once again, we can use some tricks to affect on the foaming with this polymer, for example, chain extension or blending, and this way improve the foamability. Then one other interesting polymer, PBS, polybutylen succinate. It can be partly bio-based, or there are also grades that are fully bio-based. Then it is biodegradable. There are also home compostable grades available. And also with this polymer, this low melt strength is sometimes a challenge, and we can try to affect on that to get it foamable. Or we can use blending, for example, with PLA. Then I think this is my last slide of these polymers. Two more to mention. PBAT, polybutylene adipate coterephthalate, which is a fossil fuel based, but it is a biodegradable polymer, flexible. Once again, low melt strength has been mentioned as a little bit negative thing here. And that is why typically these biopolymers are blended with each other, or this kind of tricks needed to get it foamable, or to affect, for example, this brittleness mentioned here. Then the last polymer on my list is thermoplastic starch, TPS, which is bio-based and biodegradable material. And the properties of starch vary quite a lot depending on what is the source and structure of the starch. Once again, in foaming, this mechanical strength can have some challenges, or high water absorption property. So which starts often also blending on, or some kind of structure modification is needed to be able to use it in foaming. I will finalize my short introduction and opening speech with some links for further reading. There are some publications which you can check later on. Then also there is one additional website for a project of VTT where we studied foaming. You can see some examples of products and applications there. And of course, on Vital website, there is a lot of interesting information about our project and our developments, especially now that we are entering the last month of our project. So with this, I thank you for your attention, and I wish you a nice day learning about foam injection molding. Thank you.
Thank you, Johanna. That was a very insightful presentation. So I will be presenting from PIEP the film process fundamentals and benefits. So before, let me do a very short presentation of PIEP. PIEP is a Center for Innovation in Polymer Engineering, is based in Guimarães, and so it's a research and technology organization that bridges industry and academy in the field of polymer science and engineering. We have projects, developed projects in most varied sectors in partnership with different partners and customers. And we are working in various issues such as climate transition, development of advanced materials, processing technologies, sustainable solutions, all of it to strengthen the competitiveness of plastics and the manufacturing sector. So in this session, I will present, I'll go over the explanation or the basic fundamentals of the foam injection molding, how it works, go through the benefits of this technology. Then I will connect it with the vital project goals, and next I will cover bio-based key processing parameters and how PIEP is optimizing conditions to ensure consistent foam quality. So, and then I'll finish with the look ahead at the future perspectives. So, what's foam injection molding? It's the injection molding process where a gas phase is deliberately introduced into the molten polymer during the process to create microcell structures, foams inside the part. And how does this work? So the foaming agent used in the process could be either physical or chemical, as Johanna mentioned. In the case of physical, could be nitrogen or carbon dioxide. In case of chemical foaming agents, they could be inorganic or organic, such as calcium carbonate or talc. So the physical foaming agent variation, this is accomplished by injecting the gas in its supercritical fluid phase through a dedicated supercritical fluid injector. In this phase, the gas is in a liquid-like state, obtained by maintaining the foam agent above a critical pressure and temperature, allowing the gas to quickly diffuse into the polymer melt, creating a single phase inside the barrel. After the material passes through the injection system, the pressure drops quickly, so causing high thermodynamic instability, leading to the precipitation of the gas phase out of the polymer, initiating the cell expansion. The high pressure and temperature characteristics of the injection molding process will guarantee that the physical foaming agent maintains its supercritical phase until the material is injected into the cavity. The physical foaming variant requires the setup of an injection molding unit with an external physical foaming storage container. Additional control unit is necessary to timely regulate the amount of foaming agent introduced into the barrel under pressure, guaranteeing that the gas is at its supercritical fluid phase to properly mix with the polymer. So in the physical foaming technology, a specific fuse is required to ensure proper mixing. The fuse is composed of an end region that possesses characteristic geometry to promote dynamic mixing, assuring the creation of one-phase solution. As such, the modifications are made to the end of the screw section or to the nozzle section by attaching a mixer. Due to this increment, the screw is longer than commonly used in conventional injection molding. The chemical variant does not require modifications to the injection unit, needing only the shot of nozzle. The foaming mechanism is promoted by the reaction of the chemical foaming agent in the polymer melt due to the high temperature, as Johanna already has mentioned. So some chemical foaming agents are exothermic, which can promote an early foaming, reducing the residence time for the material, and consequently the cell structure is not uniform in most cases. Also in the chemical foaming agents reaction may also result in byproducts such as water, which can lead to additional degradation of the polymer matrix and the reduction of the mechanical properties. Also, the subproduct can damage the mold cavity, and mold cavity and screw can also suffer from this reaction and can be damaged prematurely, which can influence their durability. This phenomenon can be avoided by using physical foaming agents, although requires more capital investment. However, in the long run, the physical foaming agents will become advantageous when compared to the chemical foaming agents. For both variants, it is important that the shut-off nozzle should be considered in order to prevent the foaming and the return of the material into the barrel. So why use foam injection molding? The advantage of this technology compared to the conventional injection molding are to start the cycle time reduction. It could be reduced between 15 to 40%. Why? Because packaging in the holding phase is given by the nucleation phase, and the cooling is also faster due to lower melt density and lower thermal conductivity. Another advantage is the lightweighting, so reducing part weight typically between 10 to 30% due to the cellular structure. This will lead, obviously, to lower material use and reduction costs and material saving. Also, this technology allows the reduction of sink marks and warpage due to the gas expansion that compensates for shrinkage and improves dimensional stability. The energy efficiency. Lower material and lower cycles will reduce energy consumptions. This also allows for more design flexibility, so will promote ability to mold thicker sections without defects. And last, it can also be used for thermal and acoustic insulation parts due to the foam structure. So within the VITAL project, PIEP played an important role in the development of the foam injection mold line. One of the three key technologies route being explored. Our team has been working on process optimization, material characterization, and in the integration of recycled and bio-based material into the foam injection mold process. Through experimental trials, digital modeling, and collaboration with partners such as Edener, Arcelix, Tofas, and Farplast, PIEP contributed to the adaptation of the foam injection molding technology, processing bio-based formulations, the process optimization, demonstrating the feasibility of the use of the bio-base at pilot scale. It validated material process interactions under industrial conditions, and also evaluated mechanical visual performance of the foam bio-based parts and defined the key parameters enable industrial implementation of the foam injection molding. We also helped industrial partners select the most promising formulations between several PLAs formulations that were developed during the project by our partner Florian, through the physical, mechanical, thermal, and optical testing for material requirements validation. After the selection of the most suitable formulation of PLA, We also conducted extensive physical, rheological material characterization in order to integrate this material data card in a commercial software known as Moldex 3D for process simulation studies. As well, we introduced this material data card on online material website known as MatWeb. The inclusion of this material in the Moldex 3D made it possible to perform process simulation studies for the 4 demo cases that were studied and developed within the project. After preliminary test trials for determination of the foaming agent solubility in the material to update foaming agent info versus material in the software, we conducted simulations of the process and compared with the real experimental data. In this slide, we present a comparison between simulation and experimental obtained results. On the left, we have the operator adjusting the parameters on real-time equipment, while on the right, we have the molded and simulated samples of the process with the material already characterized. We analyzed several parameters such as cell distribution, temperature, profiles, material behavior during filling, and also the solubility of the gas in the polymer matrix. In the experimental results, we observed some variability in density between samples and small temperature variations requiring some adjustments. In the simulation, we obtained a more uniform and controlled density, more defined thermal gradients, and a good estimate of the material behavior during the filling. In short, the simulation accurately represented a real behavior of the process, although some small differences were obtained, highlighting the need for continuously validating the model with real data and the fact that there is some variability on the bio-based materials. So after the results, this gave us the confidence to conduct some numerical modeling support.
Vale.
So here we can see on the slide that we worked on building the 3D numerical model in Moldex 3D for the 2 case studies on the automotive sector with TOFAS and Farplas. In this case, we supported the industrial partners in developing the mold design. In the first image, we considered the Corbac, and the second in the demo case, we also considered Variotherm. This work was also conducted for the home appliance demo case with Arcelic. And on the next slide, here we can see an example of in situ monitorization of the foam injection molding process, which allows real-time observation of cell nucleation and growth inside the mold. Although this methodology was initially applied to conventional polymers, it became extremely relevant when we aimed to transfer the process to bio-based materials, which have different rheological behavior, crystallization rates, and thermal stability. By using a transparent mold and a high-speed camera, it was possible to understand how different types of concentration of foaming agents influence the resulting cell morphology. This information was essential for adjusting bio-based formulations and optimization of injection conditions, minimizing defects such as cell coalescence and collapse. When working with bio-based polymers, we often face narrow processing windows and thermal thermal limitations. So mold sensorization and in situ monitorization make it possible to better understand how material behaves during expansion, helping us define strategies to stabilize the cell structure and ensure adequate mechanical properties. Even though this laboratory scale approach cannot be directly implemented at the industrial level due to the use of transparent molds and the low concentrations of foam injection agents required, it is extremely valuable to the development phase of the bio-based material as it provides quantitative data on cell nucleation. So to end this slide, the in situ monitorization is a learning and development tool. It enables us to visualize how it's normally invisible inside the mold, help us understand how different foaming agents, temperatures, pressures affect behavior of biobase, accelerating formulation optimization, and reducing the risk of defects when scaling up to industrial production. So during the project, when bio-based thermoplastics were processed using foam injection molding, several specific challenges arise due to the material properties that affect part quality and consistency. To start, we have the narrow processing windows that presents lower temper stability, tight margins between melting and degradation, greater shear sensitivity of viscosity, so resulting higher risk of degradation, discoloration, or gas cell collapse if conditions were not precisely controlled. Also, moisture sensitivity and hydrolysis. The biobase absorb moisture more easily. During processing, water triggers hydrolysis, reducing molecular weight. So foams will show cell coalescence, weak cell wall, loss of mechanical strength. So drying and strict moisturing control are essential. Foam structure depends on gas solubility in the polymer. So some biobases have low solubility. So this could lead to poor cell nucleation or large cell size. So it was required some nucleation agents, gas dose optimization, and precise injection profile control. Apart from PLA and looking to other bio-based materials, limit material bio-based grades optimized for foam injection molding may lead to variations. So as circularity increases, variability increases as well. So it was possible to observe some fluctuations on melt flow index, inconsistency in the crystallinity, and mixed feedstock streams may reduce the final consistency of the injected parts. So it's harder to maintain stable microcell structures and quality. So tailored formulations and process parameters development could be needed for specific applications, and geometry adjustments to compensate, for instance, impact deformation or aesthetic defects may also be considered. Regarding the process, I've more or less talked about on the previous slide, so I'll go through this slide to the next one. So regarding equipment and process optimization, injection speed, pressure may exceed limits for some bio-based polymers. Mold temperature and cool time must be carefully adjusted to control crystallization and mechanical properties. Residence time and melt volume must be carefully controlled to avoid degradation, particularly for thermosensitive materials. Gas polymer compatibility is limited for several bio-based polymers. Variation in gas dosing for injection profiles can cause instability in the cell nucleation and foam growth. Machine size, screw design, and gas delivery system also influences the foam uniformity and cell morphology, and requires careful calibration of equipments, optimizing the process parameters, and inline monitoring to ensure stable the reproducible foams. So regarding mechanical performance under foaming, even with solid skins, the foams reduce the load-bearing cross-section. There's risk of wrinkliness in PLA, resulting in lower impact and fatigue resistance. So material modification or hybrid design often is required. Foam bio-based thermoplastics parts are more prone to defects. So tooling, optimization, and skin forming strategies sometimes also are needed. For instance, inadequate tooling design can lead to loss of expansion control, and also proper ventilation in the foam injection molding process is also required. So, in the overall projects, this challenge underlined the necessity for several things. So the success of foam injection molding depends on integrating material and formulation optimization, optimization of process, tooling, machine, and digital and data-driven process control. Overcoming this challenge will ensure lightweight, functional, and consistently high-quality parts. So this challenge illustrates why vital focus was on material optimization, process optimization, digital process control, the evaluation of the recycle and bio-based content, and the application-driven design rules to unlock industrial adoption of circularity of bio-based foam parts. So this is my last slide. To finalize, the future of foam injection molding will continue in the automotive and home appliance sector, but is also expanding to several sectors due to the increasing demand of the lightweight components to improve in the car sector the fuel efficiency and to reduce emissions. Potentially in the electrical vehicles battery casing, also in continuously in the interiors and in structure components. Today, the foam injection molding is closely tied to sustainability, lightweight design, and advanced manufacturing trends, and it's expanding to other sectors such as packaging, footwear, sport equipment, and construction. The use of bio-based polymers and recycled thermoplastics in foam applications, the reduction of carbon footprint through lightweight and energy efficiency, and the development of foams with improved mechanical and thermal properties. So, and also the tailoring material for a specific performance, such as impact resistance and isolation, is a hot theme, I would say. So this was my presentation. Thank you for your attention. The next will address one of today's most pressing challenges, the recyclability. Renato Reis holds a degree in chemistry with a specialization in quality control of plastic materials from University of Minho, and a specialization of processing and characterization of materials from the same university. He is responsible for the extrusion, compounding, and advanced materials area here at PIEP. His expertise includes extrusion, reactive extrusion, and compounding, functionalization of thermoplastics and recycled materials, aimed at developing sustainable and intelligent products and process. Through his career, he has collaborated with major industrial partners such as Arkema, Repsol, Johnson & Johnson, Intertape Group, DSM Research, and Cabelt. Renato will discuss strategies to overcome the material recovery barriers in foam injection process. Renato, the floor is yours.
So thank you. Good morning, everyone. Thank you, Sylvia, for the nice words and the nice presentations. Thank you, Joanna, for the presentation. It's sure. So my presentation will be on the recyclable of the material. So yeah, sorry about this, but it's okay. Good. So the idea is discuss a bit what was the approach on Vital regarding recyclability. So we obviously we work with biomaterials, bio-based materials. Our processing equipments, our strategies usually they are more optimized for fossil-based materials. So the challenge is to use bio-based materials for instance, FIM technology are huge. But then recyclability is another challenge. So this presentation will focus on these issues. We will start with the challenges of the recyclability, the approach to improve the PLA recyclability, especially here in Vital. Then the virtual modeling approach that we take here, the compounding approach, and then in the end, the key achievements and the further technical challenges. So Vital, Joanna and Sylvia already mentioned it before. So I think there are some key issues that are enlightened over there. And it's bio-based recycled thermoplastics, recyclability and use of renewable materials. So we are, during Vital, using new materials in developing the process, but then we also need to take care about that recyclability. So the challenges that we get here and working on this, so we focus on PLA. So we know that PLA is one of the most widely used bio-based materials nowadays, but actually, and we know that from the previous studies that it shows a rapid deterioration when mechanically reprocessed, and we know that the end of life recycling remains quite limited because it's, I would say, a brand new material. Usually it's used on a single-use applications. Here we mainly focus on the long-term applications. So it's another challenge that we have. I would say that the main barriers, at least during these Vital developments, were the potential side effects that we get from the foaming process. So we know some strategies to work on the recyclability of PLA, but none of them were with foaming processes. So it was an additional challenge that we get. Of course, some processing difficulties. I would say that all of our processes are optimized through decades to fossil-based materials, and now we want to use them to work with bio-based materials, and in top of it to recycled material and use recycled material on it. So it was an additional barrier that we get, and then of course some performance limitations of the material, at least in some applications, and the limited large-scale availability of the material. And we faced that, although we have great partners on the project. Actually, there are some concerns about the amount of material that we get to work with, and of course, higher cost is also a barrier. And it needs to be addressed. So what was, I would say, the approach, at least on the vital. So we mainly focus on the digital simulation. So we use software, common commercial software for compounding, that is Ludovic. Together with it, we run some experimental validations on twin screw extruders. So they are mostly used to compounding. So I would say that create some loops between the digital simulation and experimental validation. And of course, in the end, we also try to identify the best approach for try to improve the recyclability of the PLA through compounding and through additivation. So mainly these three were the main steps that we get during the project. Schematically, and how do we run that? So we get final parts from the trials, from developments and from the industrial trials. So we get bio-based foamed thermoplastic parts. We pass them through a grinder, and we get the flakes. And then we immediately run the flakes through a twin screw extruder to make the first, I would say, the first cycle of degradation, of reprocessing. And then after that, we get the granules, and then we reprocess again 100% in the extruder. So we get, with this approach, we get a fast and a speed degradation of the material. And the idea was then to characterize and then to evaluate what was happening with material and how can we at least avoid or limit the degradation of these materials. So Ludovic, I will not go too deep on the software side, but Ludovic is used at least it was developed for fossil-based materials, and it used to simulate or at least try to anticipate what's happening in the compounder. So we need to have the characterization of the material. We put the material data on the software, and then we through the screw configuration and the processing parameters can anticipate what's happening with the material during the extrusion processes. So we get melt temperature evaluation, melt viscosity, melt pressures, shear rates. So we get all this data from what's happening inside the extruder, and we can anticipate if there is some degradation, if there is some temperature levels that are reached that we need to avoid. And with this, we can optimize both the processing parameters on the compounding and also the screw configuration, the barrel configuration. I would say the three main steps that we get was the preparation of the numerical model. We need to feed the software with the PLA characterization data. Then we run the simulation to get all the data on the material, and then in the end we can optimize both the parameters and the screw configuration. So the first step was previous characterization of the PLA. Then we feed the software with the thermal data from the material. The second step was to have the viscosities and the temperatures of the material that we want to run the simulation. And then in the end we adjust and try to identify the best processing parameters to run the simulations. With all this data on it, we run the simulations, and what we get, I would say, as expected. In the graphic that you see, we have the 5 behaviors of the 5 different materials with different cycles of reprocessing. And what we get is that we observe immediately that the melt temperature is decreasing with the reprocessing cycles of the material. So it's a clear indication that the chains of the material are being broken. So there is some degradation, and the viscosity is getting lower. That's why we get melt temperatures lower. If we go further, we also easily check that the pressures are changing with the reprocessing of the material, And then, of course, the viscosities are also changing when we simulate the different cycled materials, reprocessed materials. We also can get the shear rates, quite important because we anticipate that there is some thermal degradation of the materials. So it's quite important to monitorize the shear rate that we are imposing this material. So after, I would say, the first 30 or 35 runs of Ludovic, we also characterize these materials after the reprocessing and try to match the simulation with the reality. So we pick the materials, we run different mechanical characterization. Here we only put the MFR results, because we have previously an indication that the material is getting more fluid, and actually we can see that on the table. So we see that a major increase on the values of MVR with increasing of the reprocessing of material. It was expected. I would say it was not so expected, or at least so extreme as we get on the results. So this lead immediately to an approach of changing the screw configuration. So the next step was working on the screw configuration, keep the processing parameters optimized, and then run the screw configuration. We start with the configuration on the top, and I would say it is a standard configuration for fossil-based materials. We wanted to start with this configuration and then try to identify what was the best approach. So with the results, the approach was to, I would say, softer or lighten the aggressivity of the mixing elements on the screw. So we focus on that elements in the middle of the screw, and the two variations of the screw configuration was lighter than the first one. With this optimization of the screws, again, we run the simulations, and what we get immediately was a decrease on the temperature profiles of the material, a clear indication that, of course, the shear rates of the material was lower, and we get at least expected less degradation of the material. So we also noticed that a strange, I would say, the result of the simulation regarding shear rate. Of course, we changed the length of the mixing zone, but there were some unexpected results on these differences on the shear rate that we get from the software. With this, and then we collect, we run again some experiments, some real experiments on the compounding with these elements and with these screws, and actually we get a real change on the degradation, I would say, of the material. So in the table we compare the most aggressive and the less aggressive configurations between cycles 0, 1, and 3, and what we get, it's a major differences on the MVR results. So actually, this changing on the screw configuration, I would say it's more relevant, at least from the results that we get during the project. It's more relevant than the optimization of the parameters on the compounder, and it was quite interesting, this result. So the final step was, okay, we know that the material suffers some degradation on the recycle. We know that with increasing of the cycles, the material is getting more and more degraded, but we want to study and want to try to identify what was possible to do to avoid this level of degradation. So what we decided to test some additives. Joanna mentioned chain extenders usually are used to avoid the break of the molecular of the polymers. So we have some chain extenders, and we also have some antioxidant additives. And the idea was to try to avoid the degradation that was observed during the reprocessing. So again, we run I will not bother with you with more Ludovic graphics, but we run again some simulations. We went to the extruder to validate that, and in the end, I would say that we expected a bit more improvement. It was not what we get. So what we get was only slightly improve on the lower degradation of the material. At least when we measure the MVR, we saw that actually with the reprocessing cycles, the material is getting more less viscous and more fluid, and there are still some degradation. What we also performed was to try to, in the end, double check the mechanical properties of these materials, of this approach. And what we get, it's a slight improvement when we compare the not additivated with the additivated materials. So what we have seen, and just to remind you that we made 100% recycle of material. So we were not diluting the material with virgin polymer. We were speeding up the degradation. And since we were speeding up the degradation, we get degradation results in the end. So the results were quite interesting, I would say. It was a massive experimental and simulation study. But in the end, I think we can say that we were able to at least establish some comprehensive database PLA behavior across these multiple recycle cycles. In the graphic that you see the difference between the MVR evolution, I would say, with the conventional screw profile and I would say conventional processing parameters. And on the bottom, we see the evolution with, I would say, optimized screw configuration and parameters configuration. And as I mentioned before, we didn't get too much differences between the non-additivated with the additivated material. I think there is still some work to do on this level, but at least we get this correlation. We get this at least comfortable correlation between the digital simulation and the experimental results. It was quite interesting because we know Ludovic was previously developed for fossil-based materials. We are using it for bio-based materials, but we get good correlations on that. And then, of course, we could identify some critical recycle limits on the PLA. And it was also quite important for the project. I think we could advance on the TRL from this lab scale prototype developments for a pre-prototype scale. So we work with the twin screw extruders that are similar to the industrial ones. So I think it was a nice step that we get here during the project. So regarding the further technical challenges, I would say that Vital was quite good to identify these PLA recycle challenges. What we get during these developments was a clear batch-to-batch variation when we get the material from the suppliers. That's an issue. So when we work with bio-based materials, we are used to get the same material from the fossil-based materials. When we change for bio-based, we need to take that in account because there are some slightly variations between batch to batch. Of course, we have clear degradation trends on the reprocessing and massive variation on the properties of the material. Of course, we identify some limitations after these multiple cycles. For sure, if we add some lower percentage of recycled material on a virgin material, we get better results. But at least we know that these variations are massive. Okay, and of course, it's also that we observe because we compare the non-foamed with the foamed material, and what we get is that the sensitivity of this PLA preformed materials are higher than the non-foamed. So this is my last slide. So thank you for your attention and have the rest of a nice day. Okay.
Thank you, Renato. So let's take a short break. We'll meet again in 20 minutes to continue the next sessions on digitalization and industrial applications. So see you back. Okay. Hello, everyone.
Hello.
Welcome back.
Hello.
So we'll now dive into digitalization, how machine learning and artificial intelligence are reshaping process optimization in foam injection molding. So the next speaker is Pablo Ruiz. He's an electronic, robotic, and mechatronic engineer who is specialized in integrating artificial intelligence solutions into manufacturing process and industrial environments. He is deeply interested in transformative potential of emerging technologies to improve industrial efficiency through computer vision, predictive modeling, and data analytics. His work on several European Union projects implementing this technology has strengthened his commitment to achieving innovation in the field and contributing to a more efficient, digitalized, and sustainable industry. Welcome, Pablo. Please, the floor is yours.
Thank you so much.
Welcome.
Okay, so I will share. Can you see the presentation?
Yes.
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 Okay, perfect. Well, thank you so much for the introduction. My name is Pablo Ruiz, and I'm here to present a digitalization training session, although I'm going also to cover, of course, the part of injection molding. I think that there is a lot of interest also in studying the digitalization in other manufacturing processes. And this session is part of a synergy between the Cubic project and the Vital project. In fact, I'm involved in the digitalization parts of both of the projects. So I'm going to present the contents of this training session. Well, I want to present first of all a small project overview of both the Cubic and the Vital projects, not a very technical about all the parts that the projects have, but more focused on the digitalization parts of each one of them. Also, I will cover the current landscape of digitalization in the manufacturing sectors, as I said, not only in foam injection molding, but in general in different industries. Then to discuss a little bit about potential emerging technologies and a case of success. I can anticipate that the case of success will be related to the Vital project, where we have developed a smart system for controlling foam injection molding in collaboration with PIEP. And then to discuss about the innovation opportunities that you have if you are in charge of manufacturing systems. Well, as the project overview, I would like to present first the Cubic project. It's a project that aims to develop new bio-based materials, and not only the materials, but also the intermediate components, and validate how these components can be used to manufacture two different demonstrators. In the Cubic project, those demonstrators are automotive seats and type 4 pressure vessels. And also, once validated in these two specific demonstrators, it could be also explore how they can be applied to different sectors, such as, for example, the sports. And regarding the digitalization part of this project, we are Edener is specifically involved in the development of artificial intelligence power solutions for optimize the manufacturing processes that are involved in the development of the two different demonstrators. Then, during the Vital project, as have been presented previously in this training session, the main aim is to develop innovative processing solutions for bio-based thermoplastic, also covering the three different value chains previously presented, and the digitalization parts cover the development of a foam injection molding smart control system for the optimization of this process. I want to talk a little bit about the current landscape, not only related to injection molding, but in general, because in my experience in different processes where the part of digitalization has been involved, the main barrier, the main issue that I have realized is the data And data is closely related to the lack of sensor, lack of data gathering infrastructure, and so on. So here there are some data, for example, from reports of McKinsey, for example, that only the 30% of manufacturing companies, and this involves the technical teams in charge of these manufacturing plants, have realized the potential of the Industry 4.0. And this means that the vast majority of the manufacturing companies haven't studied how these technologies can impact their processes, and is quite related to their cost. Then the 70% of manufacturers that gather the data use manual processes to collect them, and only the 38% believe that these analytics will improve their processes. And this is the main issue, because having data is the basis to step on to the digitalization of the processes. So this is a real concern that you have to study within your own processes to study if it can help. And then the investment is of only 1.8% of the net revenue for digital transformation, having, as we are going to see in the next slide, huge potential for different aspects. In fact, in this McKinsey report, we can see how it was evaluated, how the inventory holding cost reduction could be reduced between 15 and 20%, also 15 and 30% of the labor cost productivity, 30 to 50% of machine downtime reduction, 10 to 30% throughput increase, and 85% on forecasting accuracy, and 10 to 20 in the cost of quality improvement. And this is really relevant because, as we have seen in the previous slide, only 1.8% of the revenue of the companies are used for the digitalization of the processes, while the real impact could go much beyond those numbers. But the real thing here is what emerging technologies and what different strategies can be used in order to improve and to digitalize the manufacturing processes. Here we have the three that I consider more important, that is artificial intelligence, IoT and big data, it is Internet of Things, and robotic systems. Although, for example, for artificial intelligence, we are as bored of hearing about ChatGPT and other type of large language models. There are plenty of models, plenty of approaches that maybe could be considered as more traditional, that have a real impact in the manufacturing sectors. Also, the Internet of Things and big data will provide a big support for the data gathering and collection, while the robotic system could improve different aspects, such as the automation of the manufacturing processes, the movement of materials, and so on. Specifically regarding artificial intelligence, I would like to also highlight three aspects that could be really relevant within the digitalization of the plants. The first one is the automated quality control. That could be specifically quite related to computer vision models. This, for example, when you are producing a specific part, for example, in this case with injection molding or foam injection molding, having computer vision models that supports you in identifying if the dimensions and properties of the part are correct could save lots of time from the personnel that should be doing this process manually. Also, the adaptive control based on optimization strategies is very relevant, because this is basically what have been done in the Vital project, optimizing the processing parameters in order to adapt the manufacturing process to the materials that are being used, and then to forecast the supply and the demand. For this, it can be used different predictive models in order to train a model that is able to identify what will be the demand for a specific product. And the basis of each one of these technologies are the data, because for training these different models, for refining criteria, guidelines, you have the data in order to provide a good baseline for being trained. Regarding IoT and big data, the process analysis covering statistical analysis and indicators is very important. Just if you have, for example, here the foam injection molding process, to analyze the average injection time, or different, for example, the material consumption in each injection, other kind of bottlenecks is very relevant in order to evaluate how you can reduce the material consumption, for example. Then other point really relevant is the smart inventory tracking using, for example, a RFID tags and reader. When you are in the warehouse, you have different materials located in different areas. Using such technologies could support you in the identification of the secret elements very quickly and more efficiently. And then the energy optimization. You can evaluate within your processes the energy consumption, for example, in the foam injection molding, the temperatures of the nozzle, and you can see if you can achieve a good quality of the products by reducing these temperatures, and that is directly related to the energy. And then regarding robotic systems, we have AGVs, that are automated ground vehicles for the transportation of raw materials or the manufactured parts from one side to another of the warehouses, fast packaging and sorting with pick and place robots, and reconfigurable cells for the flexible and adaptive manufacturing. Now I will going to present the case of success of Vital. In the Vital project, we developed the system. The simplified scheme is presented on the right. We developed a model predictive control integrating AI-based model for quality assessment. In this project, Edener developed two different models. One model was trained for the prediction of part properties, covering density, size, weight, and so on. And the other model was trained for the prediction of potential defects, such as shrinkage or warpage. Then those models, once validated, were integrated within a control loop. We support the operators by integrating an interface that provides decision support. And the main functionality of this system was to gather the current processing parameters via MQTT and to process them in the Vital Smart Control System. The Vital Smart Control System will identify if the current processing parameters will provide a part, will result in a part that meets both the quality and the part property requirements. And if not, the system will optimize and provide a better set of parameters in order to ensure the quality. And this was really relevant in the Vital project because we were using materials with different amounts of chemical blowing agent. So each mix must be treated with different procedures, different temperatures, different pressures. So to this end, it was really important. What we get was a solution validated in a real environment that was at PIEP facilities. The reduction in the time needed to fine-tune the foam injection molding parameters, because if it was the operator, the one that have to evaluate which parameters is the better at each moment, it will take lots more time than having this automated tool, and also to anticipate potential defective parts or deviation in the part properties, so we will be saving material. Here I'm including the human machine interface that we developed. On the left we have the processing parameters gathered from the machine automatically, the predicted outputs, and on the right we have the ones that will be provided and optimized by our system. Then here is the image of the real validation of the solution. We can see the foam injection molding operator, and on the right we have a laptop that have connection with our control system, and you can see the human machine interface. And then we validate it by performing real trials and extracting the pieces that have been considered during the Vital project. And now I would like to just mention very briefly funding opportunities, because I think that maybe the expensive cost, because the implementing some of those solutions are not direct nor cheap. So I would like to mention that the Cubic and the Vital projects are part of the Horizon Europe funding program. where both the manufacturing companies and also research centers join forces in order to develop different solutions to validate at their facilities. So I think that it would be also a good opportunity for your companies if you are interested in this kind of solutions. So this is all from my side, and thank you so much for your attention.
Thank you, Pablo, for the great presentation. So after understanding the digital side, let's hear now how these technologies are applied in real industry context. For that, the speaker will be Iram Duzanlı from Farplas. Will share practical experience and challenges from the field. Iram holds a degree in chemical engineering and is currently pursuing her master in the same field, specializing in polymer composites and lightweighting. She works as a research and development engineer at Farplas Automotive, where she is responsible for managing national and international projects focused on material and innovative technologies in injection molding applications. Iram, please, the floor is yours.
Thank you, Sylvia. I will share my screen now. Can you see now?
Yes. Yes.
Thank you. And today, Sylvia also mentioned that I will give information about real application of foam injection molding, especially focus on the VITAL project. And here, like in a brief explanation of foam injection molding, we already talked about this topic, but I want to give some brief information. And these technologies' key benefits are lightweighting of the parts, and because of this reduced carbon footprint, and also it supports for the circular economy this way. And this technology enables significant weight and material reduction across multiple industries like packaging, automotive, electronics, maritime, and consumer goods. And thanks to its applicability to various polymers, it offers wide sector compatibility and can be implemented in existing production lines. And these are some examples of industries like we can use this technology in automotive, like some engine undercover, door panel, and we can use this technology in structural parts and also packaging parts. As Farplas, we already use this technology for the engine undercover for our customers. And in VITAL project, in these technologies, foam injection molding, we try to produce two different demonstrators, two different industries. One of them is for the automotive, and in this project, we use foam injection molding with chemical and also physical foaming, and our demonstrators are double B pillar lower part and tipo B pillar lower part. And with chemical foaming, we produce double B pillar lower with PLA, and physical foaming, we produce tipo B pillar lower parts with PLA. And also Arçelik has a demonstrator with injection molding. It has some evaporation cover and vegetable tray, which also they are trying to do with PLA and also foam injection molding. In general, you know that chemical foaming is one of the technologies of the foam injection. In this method, we use some chemical foaming agent in a certain amount of the process, and after the mat mix this in the machine, we inject all on the mold, and then we take apart. And also I separate them with chemical foaming challenges and also physical foaming challenges, because in general they have some differences for the challenges. In chemical foaming, we have challenges about product quality and aesthetics because it's sometimes with chemical foaming agents, we take a poor surface appearance like severe marks and some flow lines, weld lines, because it's very hard to get optimum parts from with chemical foaming agents. And also we have sometimes we struggle with the non-uniform cell morphology and also color change, especially in other colors like not black, but sometimes in white color we can see some color changes of the parts. And our other challenges are process control and cost consistency challenges, especially with PLA material. In this project, we see some problems about the process conditions. We really need to optimize the process conditions, especially we arrange the optimum temperatures for the process because PLA degrades at high temperature. And even if we use for the chemical foaming agents, it degrades at also lower temperature. It starts to degrade, and our parts like it can be very brittle after the chemical foaming agent adding. And these also are very important points for the process. And also material and mechanical property challenges. Sometimes when we not homogeneously separate, disturb the cells in the parts, we can loss of mechanical strength, and also sometimes it's can be increased the shrinkage with chemical foaming. And these are key points of the chemical foaming process. We can say that is chemical foaming amount is very critical for the good quality parts, and also process optimization, process temperature are also very critical, and also mold suitability of the process is very critical. Sometimes we need to some technologies about the mold for the efficiency, for the more efficient for the foaming technology. And for the physical foaming, and we already talked about the physical foaming. In this process, we use some gas like nitrogen or carbon dioxide for the injection, and it's also has some challenges on the process. And this one's different from the chemical foaming because you need some equipment on this process. And it has some investment challenges because you need specialized machinery, and also you cannot directly apply this machine for the injection machine. You need some modification of the machine, and also system is more complexity in this process. And also process control also it's important in this process because you need to make gas distribution homogeneously, take a good quality parts, and also sometimes you can struggle some gas escape from the molds. And also in product quality and material challenges has in this process because sometimes you have limited applicability to all polymers, and also you can see some surface defects on the parts. And key points are this process, also amount of gas, and also process optimization, like temperature arrangement. It's very critical, and also you need to consider your machine and also your mold capacity. It's suitable for physical foaming. And now I want to give some examples about our use cases in Vital project in real examples. Like this one is our last results for getting in the project, during the project. And now we can say that we achieve nearly 8% weight reduction. And now we using 1% chemical foaming agents in our process. And also during our trials, we we try a lot of things. We try to make a process optimization. We always change the chemical forming agent amount for the best optimum parts for us. And we use cold mold in this process. And also you can see that our temperature range are quite lower than other synthetic polymers. Like maximum temperatures are 170 degrees. And also we have some unsuccessful parts. You can see in the pictures. Our most important problems about the parts sticking to the mold. And when we try to get rid of these issues, we try a lot of things for this, like we decrease the temperature, we decrease the chemical forming agent. But in this case, our problem is our mold made with for the PP material, but this PLA has lower shrinkage than the PP, so our parts dimension quite bigger than the original one. So this also caused some sticking issues on the mold. But in our last trials, we solved these problems with arranging the chemical forming agent, also process parameters. Now I can say that we solved these dimension problems with process optimization. And now Tofaş will make validation for these parts. And we are still waiting for the validation. And after that, we can see the other results for these parts. And also, I want to give brief information. I already mentioned that we have some degradation problems with PLA because PLA degrades at higher temperatures, and also our mold is our injection molding machine is quite big capacity, has big capacity. So when you wait in PLA weighted in the screw, it has degraded. You need to you cannot make wait for the after the trials. You need to continuously continue the injection. So in other parts are typo B pillar lower parts, and we use physical forming in these parts. And also you can see the difference with PLA and PLA physical forming parts. And in these trials, we have some problems about the surface defects because of we need to keep air bubbles inside of the parts, but sometimes it occurs on the surface. So we need to get rid of these problems. In our first case, we use Viotherm, fast heating and cooling system. We believe that if we efficiently study with Viotherm in our trials, we can minimize these kind of problems on the surface because for the fast heating and cooling system. And also you can see some bubbles on the cells in the parts. And in physical forming, we use nitrogen gas in process, and it's very low amount of gas, like 0.15. And also we achieve weight reduction almost 5%. And these temperatures range are quite higher than the chemical forming because we are not any problems about the brittleness of these parts with just physical forming. And you can see some pictures about other trials. We also try to arrange the gas amount of the process and also some temperature arrangement. And then when we use 2% of gas in the physical forming process, you can see some big bubbles, air bubbles on the surface. And also these bubbles are increased after several hours. Like in these examples, you can see that just after trial, there is no air bubble on the surface, but after 24 hours, we can see some bubbles occur in the same parts. And we believe that it's because of the machine is bigger for our molds. Our mold needs a lower capacity machine, injection molding machine. And now we want to make sure this statement is okay or not. Like we want to make sure that with another parts, with PLA and also physical forming, we will make some trials for this for the other big parts, and then after that we can make sure that yes, the problem is injection molding machine is bigger for our molds. And generally we have see some same problems with PIEP and also physical forming, but it's not about the material. It's all about the gas amount, but we already use a lower gas amount for this process. And now we believe that it's because of the machine is bigger for our mold. And this is end of my presentation. Thank you for listening.
Thank you, Iram. Thank you so much for your presentation. Now, so to consolidate the morning insights, we have here quick quiz, nothing formal, just a fun way to check how much we've learned. Also in a way of ending this morning session. So who's interested could scan the QR code and answer individually. There's no wrong answers here, so we are exploring how these concepts apply in real processing scenarios. These case studies help us connect to the dot between bio-based materials, process optimization, and digitalization, the three pillars of today's learning factory and of the Vital project itself. So I invite everyone here at PIEP and online to answer before heading into the lunch break and the afternoon hand sessions. So from my side, we have reached the end of the online session. Once again, I would like to apologize for the delay in the beginning of the session. In the afternoon, we'll take these concepts to the next level during hand-on session at PIEP. Here we'll get to adjust real parameters, observe the foam structures, and evaluate the recycled materials in action. The participants that are in person will go now for the lunch break, and we'll continue this journey in the afternoon. Thank you all for the participation. These learning factors has been an opportunity to bring theory and practice, innovation and sustainability. I hope you leave inspired to continue advancing in the field of the bio-based thermoplastic and materials reprocessing. So thank you so much. Thank you. Goodbye.
Thank you.
Thank you. Goodbye.
Thank you. Bye.